Okay, so we're continuing on with polynomials. In the last video, we talked about kind of how do you find roots and some ways to narrow that down. And those two methods that are helpful was Descartes' rule of signs and the rational root theorem. And so we had this polynomial, and we did narrow it down, and we saw that, hey, I definitely know I have one real root and one positive real root and one negative real root. Now, it might not be a rational number. It might be something ugly like a square root of 3, or 5 sevenths, square root of 2 minus 20, or something, just whatever. You get the idea. But it could potentially be a nice rational number, and if it is, then it's got to come out of this list, which we got from the rational root theorem. And so those are our prime candidates to find those roots. Okay, so let's go to the next page then. Two ways we can do this. So let me rewrite our function first. It was x to the fourth minus 4x squared minus 45. So our first method is synthetic division. And this is my preferred method. I just think it works so much easier and quicker. All right. And so here's what you do. Now, first of all, you got to be very careful when you do synthetic division. And this is true of long division, but you don't have as many troubles in long division. But you need to account for every power of x. So you look at the coefficients, and so think of it like this. Like I have x to the fourth, x cubed, x squared, x, and then I'll say c for constant. Okay, so my function has 1x to the fourth, 0x cubes, minus 4x squareds, 0x's, and a minus 45 for a constant. So then people do it different ways. This is how I draw my lines. The lines are just there to help organize what you're doing. They're not there to necessarily I don't know. It's not like, oh, if you drew this line wrong, it's not okay. Like, it doesn't matter. All right, anyhow. So what you do is you then pick what value you want to test, and you could test a rational value. And so let me bring those over. If I'm going to test a value, it's going to be one of these. So let me cheat here and do that. So if I have a rational root, it's going to come from there. And again, I know there's one positive, one negative, right? So here we go. Now I'm going to test one, positive one. Now, by the way, when I write a 1 here, I'm talking about the root, not the factor, right? Because if 1 is a root, then it would factor out as x minus 1, right? So be kind of mindful of that, all right? So let's see here. What you do is you always bring the first number down, okay? And then you multiply. Okay, so 1 times 1 is 1, and then you add the columns, so 0 and 1 is 1. Multiply again, 1 times 1 is 1, add, negative 3. 1 times negative 3 is what? That is negative 3, so I get, when I add, that's negative 3. Alright, 1 times negative 3 is negative 3. And so when I add, I get negative 48. Ooh, if this was a root, that would be a 0, but it's not. Okay, so I know that that's not a root. However, this does tell me something. Synthetic division is nice, because it is kind of a nice way to say, oh, well, I do know this, though. If I plug in 1, I get a y value of negative 48. So it actually does tell you that for free. But I'm trying to find roots, right? I'm trying to find zeros. So not exactly helpful. All right. So I'm going to erase this and then start over with another root, right? Okay, so let's erase it. Actually, I didn't need to erase that one because it always comes down the same way. All right, so let's say I was divinely inspired and I chose 3. 1 times 3 is 3. Add those up. 3 times 3 is 9. 3 times 5 is 15. Again, you're adding the columns. And that's 45. Ho, ho, ho! So that's a 0. So that tells me 3 is a root. Which, by the way, this also tells me then that my original function can be rewritten as what? X minus 3. So 3 is a root. So x minus 3 is a factor. But not only that, this part that is left over is the result. But everything is dropped a power because what you really have kind of done at this point is you've divided an x out, right? And so this isn't x to the 4th anymore. This is now x third, x squared, x constant. And so at this point, I have this. Alright, which is not really helpful because I still have an x cubed and I want to try to factor that down even more, right? So you can just add on and try another. Now, if I go back a page, again, Descartes' rule of signs told me there is only one positive real root. Well, heck, I just found it. It's 3. So with the rational root theorem, I should not check any more of these positives. I can now switch and concentrate on negatives. All right. And again, I could try -1, start with the easiest ones. It's not going to work. So again, we'll pretend I was divinely inspired and we'll try -3. So -3 times 1 is -3. Add them. Add them. Add them. And hey, hey, hey. There we go. So now, be careful. This did not disappear. This is still hanging out. What we did is we took this chunk and broke that chunk down more. So be careful. So the x minus 3 was still there. Then I can now pull out x plus 3. So let's maybe highlight so we can kind of connect the dots here. And what's left over? Well, now we've dropped another power. So up here it was x to the 4th. Now it was x to the 3rd. Now this is x squared. So this is x squared plus 0x plus 5. Or in other words, x squared plus 5. And I can tell you that that's an irreducible polynomial. What does that mean? Or an irreducible quadratic, I mean. That means I cannot factor that without using complex numbers, right? Because how would you factor? Well, you can even solve that. It's a little scratch work on the side, right? And so you're going to get what? X equals plus and minus square root of 5i, right? So it has complex roots, which should make sense. Because again, going back to Descartes' rule of signs, I knew I had one positive root, I knew I had one negative real root. There's a total of 4, so then we filled in the gap and we said, oh, well then there must be 2 complex roots. And there they are, and they were conjugates, the plus and minus 5i. All right? And so there we go. I now have my polynomial completely factored down using synthetic division. And let's see here, just to be super clear, this chunk came from here, right? Okay, so that's synthetic division. I think it works really slick. It's a really nice way to test values out. And then you also get that added benefit of if you throw a value in, the output, if it's not 0, is actually the y value. So Lots of good stuff going on there. All right. So now let's do long division. U So if you'll humor me for a second, some of you learned this, maybe, but like, let's say I wanted to take 250, I gotta be careful, I don't want this to be divisible by 3. 2, 5, say 251. All right, divided by 3, right? And so you would go, oh, let's see here, 3 can't go into 2 because it's bigger, so it's going to go into 25. How many times? You go, oh, 8 times. 8 times 3 is 24, and then you subtract. Bring this down, you get 11. 3 can go into 11, well, 3 times. 3 times 3 is 9, and then what do we get left over? 2. Aha, so when you divide this, you get 83 with a remainder of 2, right? Or 83 2/3, right? So that's, you know, long division with numbers, and so it's kind of the exact same process with polynomials, right? It's just we struggle with it because I know nowadays we don't really emphasize long division that much anymore. But let's do the same thing. So it is what? It is x to the 4th. Now, I don't need to put in 0x cubed, but it is kind of helpful, and you'll see why. Minus 4x squared plus 0x. Again, don't really have to put that in, but helpful. And now you're going to try to divide. Now, if I think 3 is a root, then x minus 3 is a factor, and so I'll divide out that factor, right? And so when you're doing it with polynomials, though, you want things to match up, and so if I have an x, I need to cancel this out, and so I want this to match that, and so I'm going to need to multiply by x cubed. So x cubed times x, right? X cubed times x is x to the 4th. X cubed times a negative 3 is a negative 3x cubed, right? And that's why it's good to have the 0x cubed, because then you can line your powers up, right? Now, be careful. Just like in long division, though, what do we do with the thing down there? We subtract it. And we're subtracting the whole thing, and so then the subtraction actually distributes. Which is why a lot of people hate this method, because it's easy to mess up your signs. So when you distribute that negative, I'm subtracting this and I'm subtracting this, but a negative times a negative turns that positive. Alright, so now x to the 4th minus x to the 4th is 0. And then now I get a 3x cubed. And then I could bring everything down if I want. And then wash, rinse, repeat. So now that's a 3x cubed. So to get, I need to make it match. So I'm going to multiply by 3x squared. 3x squared times x is 3x cubed. 3x squared times negative 3 is a negative 9x squared. But again, I need to subtract that, and you distribute the subtraction, and so then your signs change down there. That's how I think of it. Other people do it differently. I don't know. Whatever works, as long as you get it right. That's 5x squared plus 0x minus 45. Right? And so then now what? I need 5x squared, so then I'll say plus 5x. 5x times x is 5x squared, because I want those to match, because then when I subtract it cancels, right? 5x times negative 3 is negative 15x. And then subtract, so sign change, sign change. And if you prefer, we can cross these out, right? I don't know. Don't need to, but makes me feel better. 15x minus 45. All right. Last but not least, I can still go another round. Because if I did 15 times x is 15x. Oh, 15 times negative 3 is negative 45. Change the sign, because again, subtraction, distribute. 0. All right, that tells me that that was indeed a factor. And so now my result is what? X minus 3 times x cubed plus 3x squared plus 5x plus 15. Oh. And then I could try to break down this chunk by taking it and doing long division on it. But, oh man, it is painful. It takes longer. There's a lot more signs involved, so it's so easy to not distribute right or whatever and then screw up a sign. So long division, it's helpful, but it's a pain. Synthetic division, I think, is just so much easier. All right. Yeah, that's how I would go about doing it. There is one disadvantage, though, okay, of synthetic division. Synthetic division only work for single factors, linear factors. In other words, again, remember, testing that out as a root is equivalent to this factor. Testing that out as a root is equivalent to this factor. So you can only test a singular number, which means as a factor, it's this linear factor. Okay? I can't test out, like, what if I had, like, x squared minus 2 as a factor? You can't test that out with synthetic division. Okay? Can't do it. All right? It's got to be a linear factor only. So that is one limitation. Unlike long division, I can stuff whatever I want out here, out in front, and work on it. And so that is one advantage of long division. It's going to work no matter what you put out here. You can go through the process and get the results. So it's not limited in that respect. So that is a nice bonus. All right. But there you go. Those are two techniques, and they can help you then bring things down, factor them out, and help you figure out, okay, these are my roots. This is what's going on. Right? Okay. So with that, our next video, speaking of roots, let's talk about the topic of multiplicity and what that means in terms of the graph and how we can identify the multiplicity of a root. So check that out for your next video, and we'll just keep going with polynomials.